On 213's assignment 2, problem 12, we have a problem that a lot of people struggle with. I think for the most part, actually people do quite well on the first part of the problem. It's really part D that ends up being the biggest part of the problem. Basically, you've got here people recording information about if a Canadian has had at least one cup of coffee a day. So if you had two, three, four, five cups of coffee a day, you're just saying yes. The question being asked is, have you had at least one cup of coffee? Yes or no. So if you've had one, that counts. If you've had 17, that counts. So it's just if you haven't had coffee or if you have had coffee. So you could really kind of get around this at least one cup by just saying, have you had coffee? Or if you have you not had coffee. So I'm given some sort of probability. I don't know what your number is going to be, so I'm just going to say that it's X. Then if you're asking two people if they've had coffee today, then that would be the probability of yes times the probability of yes, because I think how much coffee somebody drinks should be independent of how much coffee somebody else drinks. So being independent, we can just multiply these probabilities together to get the probability that both people would have had a cup of coffee out of two. So what about neither of the two having coffee? Well, that's hopefully quite simple as well. Instead of having this being the probability of saying yes, then one minus this would be the probability of saying no. And if both people are saying no, then that's just the probability of no times the probability of no, or 1 minus x squared. Question gets a little bit trickier here in part C when you're actually not talking to two people anymore. You're now actually talking to three people. And so now you're wondering what the probability that at least two out of the three has had at least one cup of coffee. So there's a lot of at leasts going on here. I think making random variables with let statements helps simplify the problem. So here, when I say let y be the number of people out of three who have had at least one cup of coffee, then out of three, the number of people that could have had at least one cup of coffee is zero, so none of the three, one out of the three, two out of the three, or all three out of the three. What we're particularly interested in is at least two out of the three people having at least one cup of coffee. So that means here exactly two out of the three plus exactly three out of the three. So here, if y, or the number of people out of three who are going to have at least one cup of coffee, is at least two, then we should try and find out what the probability of exactly two out of the three having a cup of coffee, at least one cup of coffee, or or having all three out of three. So we can start to use some of the counting skills that we've been talking about earlier in the term by saying out of the three people, two of them have had a cup of coffee. That's just letting us know the order that this could have happened. Could have been the first and second person, could have been the first and third person, or it could have been the second and third person. So three choose two will be three. And then you've got the probability of having the cup of coffee. There are two of them. So here, probability of coffee to the power two. And the probability of not having coffee, there was one out of the three that didn't have a coffee. So putting this all together, you will get the probability that exactly two out of the three people had coffee. You can use the same pattern for trying to find the probability of exactly all three people having a cup of coffee. Out of the three, all three of them had a coffee. And so here, the probability of having coffee to the power three and the probability of not having coffee to the power zero, because all three out of three. So if you add that together, you should probably get at least two out of three. I think where the real confusion comes in this question for most students is in part D, where you're saying, let's say you're not talking to two Canadians, let's say you're not talking to three Canadians, let's say you're talking to some arbitrary n amount of Canadians. Okay, so what I'm doing here is saying, let n be the number of people out of, sorry, let w be the number of people out of n. Is it 15? Is it 130? Whatever. So here, how many people could have been successes? There could have been zero. All of them have not had any coffee. One of them, or two, or three, or four, or all the way up to possibly however many n is. Okay, so very similar to out of three, except for we now don't know what the maximum number is. It's arbitrarily some number n. Okay, so if we want to have at least one person out of n who has had at least one cup of coffee, what we would like to do is to find the probability of exactly 1 out of n, plus exactly 2 out of n, plus exactly 3 out of n, plus exactly 4 out of n, all the way up to exactly n out of n. We can't exactly do that though, because we don't know how many people have actually been asked. Fortunately, we can use the law of complement here to say, well, 1 plus 2 plus 3 plus 4 plus whatever, all the way up to n, could be calculated by instead of focusing on what is and adding them up, focusing on what isn't and doing 1 minus that. So if I say 1 minus having no cups of coffee, that will actually be the same probability of at least one person having a cup of coffee. So here, the probability of at least one person out of n having a cup of coffee is actually the same thing as 1 minus 0 out of the n people having a cup of coffee. So I'm going to use this pattern here that I talked about in part C to say this would be 1 minus n choose 0, and then the probability of coffee to the power 0, and the probability of no coffee to the power n. Anything choose 0 is going to be 1, so this term can kind of go away. N choose 0 is just going to be 1. X to the power 0 is also 1, so the only term that remains is 1 minus x to the power n. So here then, I can see that the probability of at least one person out of n having at least one cup of coffee would be 1 minus x in brackets to the power n. Now here, they're saying that they want this probability, that is the probability of having at least one person out of n having at least one cup of coffee, to be a third at least some percent, so some probability. So here, I don't know what your number is going to be, so I just said set it to be at least whatever your number is. So here, I am now going to set this equation equal to the number uh, that I want my probability to be. And now what I really want to do is solve for n. Excuse me. Here, this prob is actually a known value. It's going to be this number from your question. And remember, this x is actually a known number from your question as well. It should be right here. What we're really trying to do is solve for n. So I'm going to try and isolate this equation for n, but the thing that you'll notice is n is actually in the exponent, so the only way to solve for n is to use logarithms. So what I do is here I'm going to move this part of the equation onto the left side of the equation, and I'm going to move this prob onto the right side of the equation. So I'll do that by adding this onto both sides. Okay, so I get 1 minus x to the power n on the left side. And then here I'll subtract probability on both sides. And so I'll get 1 minus probability here. So this should be a number that is actually solvable. Again, we're trying to solve for n. What I do on the left side, I have to do on the right side. So I'm going to take the logarithm of the left side and the right side. And the nice property of logarithms is that an exponent with a logarithm can be written as a multiplication. So here, the log of 1 minus x to the power n can also be written as n times the logarithm of 1 minus x. So here, what you can do is basically take this exponent of n, and because I've taken the logs of both sides, I can actually say that's the same thing as n times that. Well, at this point, I can isolate for n quite easily by just taking this log 1 minus x and putting it onto the right side of the equation. So here, my n should then be log of 1 minus the probability divided by log of 1 minus x. It really doesn't matter what the base of this log is, as long as here the base of this log in the numerator is the same as the base of the log in the denominator. So whether you choose log base 10 or log base e, make sure that you're using the same base log in the numerator as in the denominator. One final thing here is n is truly the amount of people. So we realize that n couldn't be some decimal number. It couldn't be 17.333. Okay, so there are no such things as having 17.333 amount of people. So here, when you're trying to have at least 97% of the probability of being at least 1 out of n having at least 1 cup, then we know that this n cannot be given as some digit representation. It will have to be, as the question says, in an integer, a whole number. Which integer should you choose? Well, here, if you round down, then that's not going to give you the probability of having at least this amount of certainty. So what you'll have to do is no matter what n you get here, say that it was 17.3333, you are going to round up to 18, not round down to 17, because we want to have at least this much probability, and we know that there's no such thing as decimal amounts of people. They would have to be whole number amount of people. I hope that helps, and good luck.